Hi everybody. Hope your revising's going well. I just wanted to do a short video on accumulating and discounting. Mainly how we apply the this thing called the principle of consistency. So we have an accumulation factor between point S and point T, and we say, well, let's have a look at that on a line. So we say here's T and here's S, and then we have some sort of interest rate, say an I per annum effective. If S and T are measured in years, we can say this accumulation factor is 1 plus I to the power of T minus S. So this principle of consistency, so I'm just going to put principle of consistency, says that for any number of points in between S and T, I've just said one point here, R, if we've got an effective rate of interest, then we can break this whole period up into smaller periods. So where I is applied across the whole of the period still, we can see that each of these becomes 1 plus I R minus S, and this one becomes 1 plus I T minus R, all measured in years. And then we can say that that is equal to that multiplied by that, and then we can put some interest rate functions in the I. And of course here with the rule of powers, where we add these together, where we've got the common factor here, so 1 plus I T minus S. So it in fact equals that, because I is constant across both periods from S to R and then the period R to T. Now, why are we interested in this? Well, there's a number of applications. One, it's a nice way to describe, how we can break periods into smaller periods, and and how compound interest works. But I think the first thing where application where it becomes useful, really useful, is once again we'll use S, T, and R. So we're working in time units, years, in fact. And now I'm going to split that period into interest rate I. Not very clear, but that's an I. And here, that's a J. So now we've got two interest rates. And of course, if we want to look across what's the accumulation factor from S to T, you need to break into what is the accumulation under I, and then what's the accumulation under J. So nothing too scary, but we get 1 plus I R minus S, and then that's multiplied by 1 plus J T minus R. That's just a bit clearer on screen for you. There. So there's your accumulation between R and S. There's your accumulation between T and R. Now, next thing which all this is quite useful for is where, of course, then we start to complicate it a little bit and we say, right, okay, so let's do our S, R and T again. We're going to have interest rate I here, but instead of an interest rate, we're going to have a force of interest. So of course, you look at the question, you think, oh, crikey, I can't just accumulate everything at one interest rate. Then I've got to think about this force of interest, which is obviously a continuously compounding function. Crikey, what am I going to do? Well, no surprises. The accumulation over the entire period, I'm not going to write that, is 1 plus I R minus S. And then this time we multiply by e to the delta T minus R. All stuff we've seen before. So the only difference between this thing and this thing here is this part of the function and this part of the function. Good. Principle of consistency is also useful for discounting. So we've been accumulating doing that as we've seen above. Now let's do that. Let's discount. Find a present value here. Well, this is simply the multiplication sign, 1 over that. And we know that equals that as well, don't we? But we'll talk about that in a little while. So if we took this, and I'm going to draw a wiggly line, I'm going to go over to here. All right, I'll put a line there so we know everything else. So let's say we're at time t and we want to go back and discount to time s with these interest rates. So what would we do? So we can say the present value, and I'll just put a little s there just so we know it there, is equal to 1 over a s to the r multiplied by 1 over a r to the t. And then there's a cash flow, which is at time t. Okay, so this time there's a cash flow there now. So in this example, which I'm circling here, this becomes 1 over 1 plus I to the r minus s multiplied by 1 over 1 plus j to the t minus r, and then we'll multiply it by the cash flow at time t, and that's the present value at time s. So you can see how accumulating and discounting can be linked together just using this principle of consistency. And the principle of consistency is just another name for, the rules of accumulating and discounting compound interest. Okay, right, I'll clear this screen and I'll go on to I think one other application which we often see with this. So file, new, I won't save that. Here we go. Right, so I'm going to call this, so these discount functions. So the reason I bring this up is, one, is they're interesting, but two, you see them a fair bit in exams, or financial mathematics exams. So worth us just having a little bit of a look at, just for revision potentially. Not that I can say that you're going to be seeing these in your end of year exam, but you might, and that isn't a hint at all. I can't even remember what's in the paper. So please, but just learn this, because one, it is often comes up, and two, it's very useful. So these functions we usually, you'll see in questions have some sort of pretty basic form, some sort of quadratic form like this, and then we say, where t is greater than 0 and, I don't know, less than 6, something like that. Don't want t getting too big here, because obviously the discount function becomes negative, which therefore means the discount becomes an accumulation. And we're not talking about them situations on this course. So if I throw in time equals 1, so I'll put that there. V to the 1 comes out at 0.99. If I put time equals 4, V to the 4 equals 0.84. 1 minus 4 squared over 100 is 0.84, I hope. So, good. So these are our V's. Now, what do these do? So, V to the T is that. So these things always run from time 0. Now, you might get a question what says, okay, that's great. So we've been given this function here. We've been given a Vt equals 1 minus t squared over 100. So what is V between 1 and 3? So people who haven't studied this properly often just get this wrong. They often just say, oh, I know what I'll do. I'll just do V3. That'll do. Something like that. Or I'll take away V1 from it. Or it's all madness. So no, what we need to do is first of all, we'll go and derive what we do in using the principle of consistency. So we can have an accumulation factor between 0 and 3, which is equal to the accumulation factor between 0 and 1 multiplied by the accumulation factor between 1 and 3. Now, why have I done that? Well, look, we want to find this discount function here. Oh, what did we say? That 1 over v is like 1 over a, I think. Or at least we'd done an example which implied that. So let's write some stuff down here. So let's write that down. A to the 1 over 3 equals 1 over v to 1 over 3. Brilliant. Okay, so we're going to find that. Now, no, both of these here, though, run from 0. So v 0 to the 3, which is equal to v3. Remember, we said all these things run from 0, is equal to 1 over a 0 to the 3. So now, if we go and write down a to the 1, 3 equals a to the 0, 3 over a to 0, 1, which is equal to, so this one is equal to 1 over v to 3. So this becomes, and this one is 1 over v to the 1. So equals that. And then finally, we know that this accumulation between 1 and 3 is equal to 1 over 1 minus 3. Sorry, the v to the 1 between 1 and 3. So we can write that as v 1, 3 equals v to the 3 over v to the 1. Add in t equals 3 here, so v to the 3. So that's 1 minus 3 squared over 100, which is 0.91, I hope. So we can get the answer that is 0.91 divided by 0.99. So obviously that increases it a little bit. I haven't got my calculator with me, but it's obviously going to be something like 0.92 or whatever. It gives us the discount function there. Now sometimes, I suppose the final thing which is useful for, let's go and find what this number is. I'm just going to nip onto Excel. So that was 0.91 and then divided by 0.99. If I can do that, There we go. So it's let's go back to the sketchbook. So that actually equaled 0.919, I think. I'm not going to go any further than that on the decimal. Should do really, I suppose. One more, maybe that was that then, wasn't it? So good, we got that. Sometimes you get, well, what's the average annual interest between 1 and 3? So we can say now that 1 plus I to the minus 2 equals 0.9192. And I'm not going to do this because I'm running out of room, but you can see we can rearrange for I. So first of all, let's take, if we move everything around to start with, we can say 1 plus I squared, I've got my bracket there, is equal to 1 over 0.9192. And then finally, and doing the rest, we can say I equals 1 over that number to the square root and minus 1 to give an answer. See what the answer is, shall we? Should be something like 5%, I presume. So I think it was, what, let's do this properly, equals 1, bracket 1 over that to the power of 0.5. Got to put an extra bracket in there just in case. Minus 1. There we go, 4.3%. Down here, keep going to 4.3%. I should use another decimal. Let's have a look what it is. 4.30. So it is actually a 0. So put that in there now as well. Per annum. There. But that's the average interest rate. Okay, so I suppose in summary, what I wanted to show was this principle of consistency. Why we bother to study it, and the reason is it gives a nice formulaic way to understand, the power of compound interest and how we can break accumulations and discounting into discrete pieces of time, which allows us to answer, real world questions. And then I think at the end there, I just applied that to these questions related around discount functions, which can come up. Often they trick students because of the time period they run from. And then finally, bringing it all back to one of our sort of our basic things, which is finding, kind of annual interest rates. So I hope that helps. Keep studying, and I'll speak to you very soon.